everyone. In this session, I am going to explain how to solve the recurrence relation. So, usually for recursive algorithms, we are getting recurrence relation, right? So, this is a given recurrence relation. So, x of n equal to x of n minus 1 plus 5. So, here x of n is defined in terms of x of n minus 1. So, it is a recurrence relation. So, for all recursive algorithms, we can define a recurrence relation. So, how to solve this recurrence relation? So, in three ways we can solve the recurrence relation. So, the methods are first one is substitution method. We can use forward or backward substitution method. Second one is recurrence tree method, and third one is master's theorem. Out of which three, I am going to explain how to solve recurrence relation using backward substitution method. Okay, so in backward substitution method, I'm going to replace the right hand side of the recurrence relation by its expanded value. Okay, so the given is x of n equal to x of n minus 1 plus 5. So the base condition given is x of 1 equal to 0. It is already given. So whenever the n value is 1, we will get 0. Okay, this is a base condition. So now backward substitution method. To substitute the expanded value of x of n minus 1, I have to apply n minus 1 in the place of n. Okay, so replace n by n minus 1 in the first equation. So by replacing this, I will get the value of x of n minus 1. Okay, so x of n minus 1 equal to, I have replaced n minus 1 in the place of n in the given equation. Okay, so x of n minus 1 minus 1 plus 5. So x of n minus 2 plus 5. In the first backward substitution, I am getting n minus 2 plus 5. Okay, so I'm going to replace the x of n minus 1 in the given equation by this expanded value. So x of n equal to x of n minus 2. Already there is a 5. Now again we are getting plus 5. So 5 plus 5, 10. Okay. Now in second backward substitution, I am getting, so initially it is x of n minus 1 plus 5. Now it is x of n minus 2 plus 10. So once again I am going to find what is x of n minus 2, right? So again I am going to replace n by n minus 2 in the given equation. So x of n minus 2 equal to x of n minus 2 minus 1 again plus 5. So x of n minus 3 plus 5. By solving this, we are getting this expanded value for x of n minus 2. So I'm going to replace this x of n minus 2 by this identified value. So now x of n equal to x of n minus 3 plus 5 and plus 10 is there already, right? So now the x of n value is x of n minus 3 plus 5. Now we are going to compare these three steps. So initially it is x of n equal to x of n minus 1 plus 5. So minus 1 plus 5, right? I will we move one step backward to this. We are getting x of n minus 2 plus 10, right? So initially 1, here 5, now 2, 10. So similarly here 3 and 15. So every time this value is incremented by 1 and this value is multiplied by the next value, right? 5, 10, 15. So similarly, we can generate a general pattern for this recurrence relation. So by which we can get after ith iteration x of n equal to x of n minus I plus 5 into I, right? So if I value is 1, if it is a first iteration, we are getting x of n minus 1 plus 5. If it is a second iteration, I am getting x of n minus 2 plus 5 into 2, 10, right? So if it is a third iteration, I am getting x of n minus 3 plus 15. So this is the general pattern of the given recurrence relation. So we have identified the general pattern of this recurrence relation. Now we have to move to the next step, right? So we have to compare this value to the initial condition, so that we can eliminate this um, x term in the right hand side. Okay, so always the recurrence relation is defined in terms of x, again in the right hand side. So we have to eliminate this term. For that, we are going to use the base condition. So the given base condition is x of 1 equal to 0. So instead of n, I have to change it into 1, right? So here, in general pattern, I am getting n minus I, right? So I am going to compare, to eliminate this, I am going to compare n minus I equal to 1, because in base condition x of 1 is 0, right? So I am comparing n minus I equal to 1. So I value will be n minus 1. Okay, now I am going to substitute I value in the given general pattern of the recurrence relation, so that x of n equal to x of n minus, again I value n minus 1, right? So by solving this, I am getting x of 1 equal to 5 into n minus 1, right? So now I know the value of x of 1. So that is 0. The remaining value is 5 into n minus 1, right? So now we have eliminated the x term in the right hand side. So the recurrence relation gets solved, right? So 5n into 5n minus 5 is the solved equation. So x of n equal to 5n minus 1 is the solution. So if we are finding the time complexity of this equation, it will be definitely big O of n, right? So that's all, the first question. So in this question, first we have to find the backward substitution step by, in different steps. We are backward substituting the right hand side of the recurrence relation, so that we can find the general pattern of the recurrence relation. After finding the general pattern of the recurrence relation, I am going to see the base condition of the given recurrence relation. So if it is 1, the n value, if the n value is 1, I can solve this, right? So I am going to compare the general pattern value to 1, so that I'm comparing the right hand side of the general pattern n minus I to the base value 1. Okay, so now I am finding what is I. So I am replacing the I value in the general pattern, so that I can eliminate the right hand side recurrence, right? So at finally, I have achieved the final answer. So that's all. So second problem, x of n equal to 3x of n minus 1. Here also, x is defined in terms of x. So x of n, here x of n minus 1. Again, it is a recurrence relation. The given base condition is x of 1 equal to 4, right? So here, uh, x of 1 equal to 4. So we have to find the general pattern, and we have to compare it with 1, so that I can eliminate the right hand side recurrence, right? So again, the given recurrence relation and its base condition. So I'm going to apply backward substitution method. Here I'm going to find x of n minus 1, right? So I have to replace n minus, I have to replace n by n minus 1, right? So in this equation, I'm going to apply n minus 1 in the place of n. So x of n minus 1 equal to 3x. Instead of n, I am going to put n minus 1. Again, this remaining minus 1. So by solving this, I am getting 3x n minus 2. So I can directly apply this value in the first equation, right? So x of n equal to 3 into, so already there is a 3. Now x of n minus n is replaced with this value. So 3x n minus 2. So initially it is a single 3. In one step backward, I'm getting 3 in 3 multiplied 2 times, right? So again, this is n minus 1. This is n minus 2. So once again, I am going to replace, once again, I am going to going one step backward. So I have to find what is n minus 2, x of n minus 2. So similarly, I'm going to replace n by n minus 2. Now I'm getting the value 3x of n minus 3. Okay. Now I am going to substitute this in this previous recurrence relation of x of n. So x of n equal to already 3 squared x of n minus 2. X of n minus 2 is replaced by the expanded value. So 3 squared 3x into n minus 3. So 3 power 3 x of n minus 3. So I have now uh, came 3 steps backward, right? So in the first step, I am getting, in the first step, 3x of n minus 1. In the second step, 3 power 2 x of n minus 2. In the third step, I am getting 3 cube x of n minus 3. So I can, from this, I can derive a general pattern 3 power I x of n minus I, right? 3 power I x of n minus I is the general pattern I can derive from this backward substitution. So now I have to find I have to find what is the value of I by using the base condition. So here n minus I, in the base condition, I can see there is 1, right? So I have to equate this two things, n minus I equal to 1. So I value will be n minus 1. So x of n equal to, I have to replace the I value in the general pattern by n minus 1, right? So 3 power n minus 1 into x of n minus 1, right? So minus is multiplied with the internal values so that we are getting n minus n plus 1. So now it came as the base condition, right? X of 1. So we already know x of 1 value is 4, which is given in the question, right? So I'm replacing x of 1 by 4. So 3 power n minus 1 into 4. So 4 into 3 power n minus 1 is the solution. Okay. So now if we are finding the time complexity of this recurrence relation means I will get 3 power n, right? So that's all about second question. So third question. So x of n equal to x of n by 2 plus again n. Okay. So this is also a recurrence relation. X of n is defined in terms of again x of n. So the given base condition is x of 1 equal to 1. So, but here there is a difference. They are giving, we have to find the value of n equal to 2 power k. That is also given. Okay. So we have to solve the question as usual. So the given is x of n equal to x of n by 2 plus n. X of 1 equal to 1. N value is 2 power k. Here I'm going to replace n value by 2 power k. Okay. X of 2 power k equal to x of 2 power k by 2 plus 2 power k, right? I am substituting 2 power k in the place of n. So now 2 power k, this division can be represented as 2 power k minus 1, right? So now replace 2 power, this is a recurrence relation. When we are replacing this n by 2 power k, given 2 power k, right? Why this step is because it is given, right? We have to solve n equal to, solve for n equal to 2 power k. Okay. So 2 power k equal to x of 2 power k minus 1 plus 2k. So this is also one recurrence relation because x of 2 power k is defined in terms of x. So I'm going to find what is x of 2 power k minus 1. So for that I'm using same equation, but I'm going to substitute 2 power k minus 1 in the place of 2 power k, right? So in the backward substitution, I'm getting x of 2 power k minus 2 plus 2 power k minus 1. So similarly, I'm going to do the same thing. I'm going to apply the value of x of 2 power k minus 1 in the previous equation, so that I'm getting x of 2 power k minus 2 plus 2 power k minus 1 plus 2k. Okay. So now again I'm going to find what is 2 power x of 2 power k minus 2. So I go to replace 2 power k by 2 power k minus 2 in the first equation here, right? So I'm getting x of 2 power k minus 3 plus 2 power k minus 2. So now I have find the x of 2 power k minus 2 value. Once again I am substituting the 2 power k minus 2 value in the previous um, original equation. Okay, so x of 2 power k is changed into x of 2 power k minus 3 plus 2 power k minus 2 plus 2 power k minus 1 plus 2 power k. Okay, so now we can compare to get a general pattern. We have to compare all these things. So initially it is x of 2 power k equal to x of 2 power k minus 1 k, right? Here minus 1, here k. In the second thing, here x of 2 power k minus 2 plus k minus 1 again plus k, right? So here k minus 1 k, here k minus 2, k minus 1 k. In the third backward substitution, I am getting k minus 3, k minus 2, k minus 1 and k. So now from this we can find a general pattern. In the ith iteration, definitely I will get x of 2 power k minus I. So k minus I minus 1, right? So by multiplying this minus into internal symbol, so we will get minus I plus 1. Okay, so similarly it will be expanded up to 2 power k, right? So this is a general pattern of the given equation. So initial condition, now we have to find the value of I by comparing with the base condition, right? So I have to find the base condition. Base condition is x of 1 equal to 1. So I have to compare the value with 1, right? So here it is 2 power k minus I. We have to compare this with 1, right? Already this is 2 power k minus I. The value is 2 power 0. Why I am putting 2 power 0 instead of 1? So value of 2 power 0 is equal to 1, right? So but I have to make it similar. Okay, so that I have used 2 power 0. So now k minus I equal to 0. I can easily find the I value, right? So I equal to k. So now I can use this I equal to k in general pattern. Okay, so that I can eliminate this x, right? So 2 power k equal to x of 2 power k. In the place of I am going to use k. So k here k minus 1, sorry, my k minus k plus 1, k minus k plus 2 up to k. So here it will be 2 power 0, 2 power 1, 2 power 2 up to 2 power k. So now we know 2 power 0 is 1, and we also know x of 1 value will be 1, right? This is a base condition. So I have removed by this substitution I have removed the uh, recurrence in the right hand side. So x of 2 power k equal to 1 plus 2 power 1 plus 2 power 2 plus up to 2 power k. So from this uh, I have to know um, to simplify this I have to know one formula, that is 1 plus r squared plus r power cube up to r power n. The formula is r power n plus 1 minus 1 r minus 1. Here the r value is 2. So 2 power, this is up to 2 power k, right? So 2 power k plus 1 minus 1 divided by 2 minus 1. So by solving this, we are getting 2 power k plus 1 minus 1, right? So 2 minus 1 is equal to 1. So the remaining thing will be 2 power k plus 1 minus 1. X of 2 power k equal to 2 power k into 2 power 1 minus 1. So now we already know initially we get n equal to 2 power k, right? We have started with this only. So the given is n equal to 2 power k. So I am replacing the value at the n by n so that I can find the complexity of this problem. So this 2 power k is replaced by n. Now x of n equal to 2n minus 1. If I am telling the time complexity of this problem, I can say big O of n. Okay. So okay. Similarly, in this problem, they are giving n equal to 3 power k. Okay. So similarly, we can do the backward substitution, and after 3 substitutions, we can identify the general pattern of the given problem after ith iteration. So then to eliminate this recurrence at the right hand side, we have to compare this value to its base condition given. So by base condition is x of 1. So I am going to compare this value with the 1. So 3 power k minus I equal to 1. So 3 anything power 0 is equal to 1. So I am comparing this with 3 power 0. So k minus I equal to 3 power 0. K minus I equal to 0 and I value will be k. So similar to the previous problem, I can solve this. So x of 1 value is again 1. So by the base condition, I can easily solve the right hand side recurrence. Okay. So 1 plus k. So already we know n value is 3 power k. So we have to find the value of k so that I can give the final solution in terms of n. So I'm going to replace this k value by n. So I can use here n equal to 3 power k. So I can take log, right, on both the sides so that I can eliminate this this value. Eliminate this value. So I'm taking log to the base 3. Okay. So now the k 3 power k can be written as k into log 3 base 3. So k value will be, so log 3 base 3 value will be turns into 1, right? So k value will be log 3 n. So we have find the k value. Now I can change the given equation x of n equal to 1 plus log n, right? So with this we have solved the recurrence relation. If it is if we are finding the time complexity of this, we can say big O of log n, right? Log n to the base 3. So in this way we can solve any recurrence relation. So thank you.